sponsored webinar is sponsored by Providence Consulting and reflects their views, opinions, and recommendations. It is titled, Can PHA Be Big Data? How to Make PHA Data Work Smarter. It'll be presented by Patrick Nonhoff. And without further ado, Patrick, we hand it over to you.
Okay, thanks. Well, I appreciate everyone attending, and hopefully we'll get some good knowledge share. Today we want to talk about whether PHA should be considered big data, and in line with that, how to make your PHA data work smarter. So the overview, we'll go ahead and save the answer till now. The answer is yes. Process safety information, PHA information should be considered part of a big data scheme. So big data is real hot in the industry right now, and we feel that PHA information should be included in that view and in all things big data. Today we'll talk about how that should happen. First, we'll just talk about today's PHA process. How are PHAs performed today? Then we'll talk about big data. So we might have big data folks on the line. We may have some PHA folks on the line. And we also might have people that are unfamiliar with either. So we're going to talk a little bit about the basics of each of those areas, both PHA and big data. Then we'll talk about, since we are suggesting that PHA information should be included as part of big data, what are the limits? Why is it not naturally included today? And we'll talk about some of those limitations. And then obviously those limitations do have a solution, and we'll review those solutions. So to start off, we'll just talk a little bit about what the current state of affairs are for PHA information. So today, a basic PHA process hazard analysis goes through some common steps. These steps can be different for different clients, they can be different for different organizations, they can be different for different owner-operators, but generally speaking, they follow the same process. So when you're in a process hazard analysis, the goal is to identify risks. And the way you do that is you identify causes, things that could go wrong. What can go wrong in a petrochemical facility? When you identify those, you then talk about, well, what's the consequence of those things going wrong? And it could be anything from maybe just a slight overpressure of piping that results in a gasket leak to an incredible runaway reaction that results in some type of catastrophic failure of a vessel, and then all the associated impacts of those consequences. So most companies then risk rank that cause-consequence pair. So each cause could have a consequence or multiple consequences, and then they rank what those scenarios are. A lot of companies really rank the unmitigated risk. They say, if we didn't have anything in place to keep us safe, how would that look? What is our risk ranking? And we'll talk a little bit about that in a moment. Then they look at the safeguards and they really ratchet down that risk ranking based on the safeguards that are available. And then that gives them a mitigated risk. And so they then assess that risk and determine, are we risk acceptable? And if not, then they can make recommendations to physically change the facility or maybe put additional administrative controls in place, but they can do something to help mitigate that risk. So that's the general process. Different companies may swap the order of those. How they define the consequence may be different, but generally speaking, that is a PHA process. So we'll walk through an example to really kind of provide even more clarity of how a PHA is performed. So this is just a simple distillation column. So everyone on the call probably has a pretty good awareness of how a distillation column operates. Well, in a PHA, you would kind of understand what this distillation column is, and you'd say, okay, the maximum allowable working pressure of this system is 175. We normally operate around 140. And the cause, the hazard evaluation, is going to seek out a cause, something that could go wrong. And the one that they identified was blocked outlet on the overhead line. So you take the overhead, it's a full condenser, you condense in it, you put it in your accumulator, and then you put some to the reflux, and then you send some out to final product. This scenario, the cause is you block that outlet. So what does the PHA information look like? That information is typically captured, and there's some industry-leading softwares that are used to capture this information. And a lot of people use simple Excel spreadsheets. Some people even put it in Word documents. But generally speaking, the information that is captured for the cause is pretty common. And so what you would see is that they would assign it to the unit that you're in. They would say, okay, we have a node, so they break down the facility into study sections. Those are called nodes. And then they have a series of deviations, and this one would be a no flow, so it's a way to block the flow from somewhere. And then they would put free text description as to what went wrong, the cause. And so you can see that cause is overhead liquid control valve, FC109, loses instrument air and fails closed. Or it could be a number of things that really close that valve. This particular PHA, this particular team, decided to list it in that manner. After the cause is captured, then the team will spend some time discussing what that consequence is. So in this case, they looked at that consequence, and the team decided, well, the way to evaluate this is, well, we've got a blocked outlet, and so we're going to increase the pressure of this column system because the way that it operates, the way that we expect the thermodynamics to respond, is that we're going to increase the pressure of this system to much greater than the MEWP, and they kind of said, well, this could get as high as 2 or 3 times the maximum allowable working pressure of this equipment. And that would ultimately be vessel failure. So the team would work through that, come up with what they feel is the consequence, and then assign it appropriately. After they do that, what you now have is you have a cause and you have a consequence, and most organizations have a risk matrix. So the risk matrix is just two axes. On one axis is your severities or your consequence severities, and the other is the frequency or likelihood of the scenario. And different companies will measure the likelihood of the scenarios in different ways, but ultimately you have the severity and the likelihood of what could go wrong, and this would put us on our unmitigated risk. Again, not all companies do it the exact same way, but generally speaking, you can come up with an unmitigated risk. So this just says, if this goes wrong and we don't have anything to protect us, what would that look like on a risk matrix? Well, if you have a catastrophic failure of a vessel that has hydrocarbons in it, and it's simply based on, and you define the frequency based on the failure, you could say, well, that's going to happen occasionally, and that severity could be catastrophic. And people define catastrophic as, let's say, a fatality. So in this scenario, we could say this could happen ever so often, and we could have a fatality. Obviously, that is not where owner-operators want to be. So then they would start to discuss the safeguards that they have available to them. And in this particular case, this particular setup, they have a shutdown, pressure shutdown, that would help prevent this overpressure. So on high pressure, it shuts off the heating source, maybe cuts off the feed to the column, but it puts it into a safe state. Additionally, you also have a relief device, and that relief device could be sized for this particular scenario. So then they can say, okay, well, those help mitigate our risk, and the way they help mitigate the risk is it really reduces the likelihood of this scenario occurring. So there's rule sets or procedures that organizations put together to help you understand how to now lower your risk, including those different safeguards. And so they apply those rules and they come up with a new risk ranking, which is a 2. So graphically, you can see on that risk matrix that different values have different color codes associated with them, and this is very common. So the higher risks, 3, 4s, and 5s, typically are not acceptable, and lower risks, 1 and 2, are acceptable. So in this scenario, if we didn't take credit for any of the safeguards, we're at an unacceptable risk, and then once we add in the safeguards, it lowers to an acceptable risk. That is an example of how PHAs are currently evaluated and documented. So the documentation is pretty common in the industry, and what they put in there is quite common. The two things that are really interesting, if you are very interested in data, the two more important fields that are populated in a PHA are cause and consequence. And when I say important, everything falls from those two fields. Those two fields, as you saw in the previous slides, were free text fields. So there wasn't any set structure. There wasn't any data mask that they had to follow. It was just as if they were speaking and typing at the same time. So if you look at it as a whole, you can see that this is kind of color-coded to demonstrate the information that is generated in a PHA, and this is one scenario. So in that orangest color, kind of the UT Longhorn orange, you can see that those are the cause information. And the most important information that you have in that section is the cause itself, the description of what went wrong. And then the green is the risk and the consequence. So in the consequence, it's free text. There's not necessarily a data mask or a prescribed way to capture those consequences. Thankfully, a lot of the other fields are organized in a pretty structured format, such as your severity, your frequencies, and your risks. But not cause, consequence, or even how you may have captured your safeguards. So you're capturing some information, but it's relatively unstructured. Okay, so let's talk real quickly about big data. So now we've kind of set the tone of what PHA does and the data that PHAs generate and how they generate that information, how they capture it. Now let's talk a little bit about big data to try to start to associate how PHAs may or may not be considered big data. So when you start to think about big data is defined by a series of V's. People use different V's, but the three most common definitions of big data are you have some voluminous amount of information. That information comes in a variety of formats. It's coming at you at a very rapid pace. And the idea of big data is to use that type of information, huge volumes of a variety of information that's coming at you very frequently and quite often, and then to use that information to accomplish truth in what that information tells you so that you can drive value. So the idea is take a bunch of information and find ways to determine what the truth of that information is and then apply it so you can increase the value in your facility. So using that protocol, let's talk about PHA through the lens of big data. How does PHA fall into this? Well, volume. We just looked at one scenario. I want to give you a flavor of a large petrochemical facility. On average, a PHA will have anywhere from 1,500 scenarios to 2,000, and that is not necessarily a huge PHA. That is a common-sized unit in a large petrochemical plant. Well, large petrochemical plants have about 30 of these units, sometimes even more. So you multiply that up, you have at one facility 45,000 PHA scenarios. Now remember, that 45,000 is just a count of scenarios. That's not even a count of your data fields. From the screen a couple slides back, you have multiple fields of each scenario. Each scenario has upwards of 15 fields of information. If you look at the past 5 years, you have to do a PHA every 5 years, that means that every 5 years you'll have about 45,000 PHA scenarios. I think people, the industry in particular, really focus on a 5-year period. And they forget you've went through PHA cycles as many as 6 times. Given that the OSHA standard was promulgated in 1992, it's possible that you have had 6 cycles of PHAs. So if you multiply that up, we're talking about hundreds of thousands of scenarios. Multiply that by the pieces of data, the actual data fields that are captured in each scenario, we have millions of pieces of data. Clearly, PHA data is voluminous. Variety. Well, variety is about the picture of all the different information that you have coming at you and how you can link it together. So in a PHA, you obviously have a lot of different fields. Some of those are structured, some of those are not. But you have a large amount of information coming your way. You'll also use a lot of Excel spreadsheets. You could use some PDFs. You're using a lot of drawings, P&IDs. So all the information that is used in a PHA definitely is high variety. However, the thing that's of interest from a variety perspective that I want to focus in on is the variety of how it's captured. We used a few examples earlier of just cause and consequence, and since there's no structure, the variety of how that information is captured can prove to be a problem. We'll talk about that. Velocity. Velocity is one of the key components of big data. So when I think of big data, I most commonly associate that with data historians and trending and data mining from operational facilities. That is true velocity of information. When your data historian is capturing your pressure measurement, your temperature measurement, your flow measurements on a periodic basis, it could be as frequent as every few seconds to as every few minutes. But if you're capturing that, your data historian, and you're doing a lot of data mining, we're talking about just an immense amount of data. So PHA doesn't have the velocity, but the idea is how can you use other information that may not have the velocity and tie it to the information that does have this high velocity. It is not uncommon in the big data world for people to say, oh, I'm going to identify when we have pump failures. They may have it in their mechanical integrity systems, and they'll say, yep, we had a pump failure on January 3rd, March 4th, April 10th, and they'll start to identify those and then take all the big data, all the operational information, and then these tools, these amazing big data tools will start to show you trends that you cannot make sense of with your own abilities. You have to have an incredibly exhaustive big data schema in order to understand how that big data, how all those operational parameters impacted those failures. So the velocity of PHA information isn't there, but a lot of the consequences that you're identifying, you should be able to start to relate the huge amount of velocity of data to specific consequences that you have in your PHA. So then what that does is you're able to use that PHA data to prove out the accuracy of your evaluation. Hey, when we said that in our PHA we had this cause, we expected high pressure, we expected our relief device to lift, we expected this to end up in this state, we expected our process to end up in a specific state. You could use all of that huge amounts of information from your data historian to prove out whether your analysis was correct. That obviously also allows you to do a lot of additional information, a lot of additional evaluations. We're going to talk about some additional information you should capture that allows you to increase the value. Specifically, we're going to talk about some data comparisons, how to capture and leverage the knowledge that sits in all these PHAs, and also how to use that as some more predictive modeling. So, in order for the PHA information to be included in a big data model, what are some of the problems that exist today? First, I want to make sure that we give credit where credit is due. For the past 25 to 30 years, the industry has done an excellent job, a really amazing job at facilitating their PHAs. The industry does PHAs incredibly well. They're timely, they're very disciplined about it, the evaluations are very solid. From my experience, they do put the right people in the room when they're performing these PHAs. You've got the right people, the right knowledge. However, when you capture all this data, you don't manage the resulting information well. So while you're doing these very well, I do not believe the industry recognizes the vast amount of value that you are capturing. The amount of information, the amount of value that you're capturing in these PHA systems is immense. And that's what we're going to talk about for the majority of the rest of the presentation, is how can we extract that value out of this big data set. So the ins and outs of PHA. We've talked about this, but I'm going to go through some of these in detail. Some of them we haven't touched on yet. So when you have a PHA, one of the things that goes in is just amazing amounts of man hours, anything from your preparation to the actual occurrence of the PHA in the meeting time. These are not inexpensive activities. So then you have an expertise repository. You pull in some of your best and brightest to participate in these studies. And then there's a lot of resources that go into these studies. And what you get out, generally you get up-to-date process safety information. You get a massive report. Most PHA reports are printed, slapped in a binder, and put on a shelf. The two most commonly used deliverables of a PHA are your recommendations list with action plans. When we talked earlier, we said that if you end up in an unmitigated risk that is not acceptable, well, you make a recommendation, and you recommend something to fix that unmitigated risk. And then the last is generally you have safeguard lists or independent protection layers that then are used to make sure that you maintain those in a certain way to mitigate the risk that you've identified. So, what's the problem? With the ins and the outs and the existing information, what's the problem with our PHA data now? And this analogy I really like. If you think about a PHA, it really is a snapshot in time. It's almost like you took a Polaroid picture and put it in your family album that you could later on, get out, dust off, and reminisce about that period of time. And while that's really nice, it's not very useful when you're talking about hazard information. So it's kind of a single-focused, it's really a snapshot in time, and it's not very useful except for those few things that we just mentioned, the lists of safeguards or independent protection layers, and any recommendations that come out of it. Other than those two things, this immense amount of time, effort, and energy that went into the PHA is not leveraged. It is not used. So you have some of your best and brightest, smartest, and most capable sitting in a room documenting knowledge that is not used. So how can we make it more useful? How can we leverage that information? Well, we have to have a paradigm shift. We have to start thinking about it as less of a snapshot in time and more about this high gigapixel view that you can zoom in and out of, sort, categorize, slice and dice in 10 different ways. So kind of multiple layers. You want to be able to compare and cross-check different PHAs, different results. And you need to be able to access that information. So what is the limitations right now that prevent that? The barriers are multiple, but I believe they're primarily two. Lack of accessibility and lack of structure. As I mentioned, lack of accessibility is these files, this information is not easily searchable. Now, is it all electronic? Arguably, yes, but because there isn't any structure to it, you really can't search for it. If you're looking for a specific failure, being able to do a free text search, you probably don't have Google on your PHAs. You can't Google a specific word because it knows it can translate what the team was thinking. So if you don't know that they used vessel 100 versus the debutanizer, you may be lost because you don't know quite what to search for. Additionally, that data is really stored in standalone software. And the most common systems out there are pretty restrictive. They don't just allow everyone to get in and look at that information. Understandably so, maybe. They want to, control the access to their software, and they want to increase their licensing. Additionally, not all companies use one standard software. You might use a lot of different softwares. You could use Excel spreadsheets. You could use Word files. So it's not all in one similar structure. Most commonly, these PHAs are printed out, slapped in a binder, put on a shelf. Kind of put the picture in the family album, and someday if you want to reminisce, you can look at it. The lack of structure is also a problem. So you really need to have a paradigm shift to change from free text fields where you're embedding really important information to maybe breaking it out. So the structure is you capture probably process fluids, equipment that is involved, different safeguards and how they were protecting the scenario and how they mitigated the risk. And then the consequences has immense amount of information. But it's all free text fields. There's no structure to it. There's no data mask. There's no categorization. And so you're not really able to use it. So you can't get to it. And even if you could get to it, it's not structured in a way to where it's very usable, especially in a big data model. So what does that result in? What that results in is a lack of consistency. So without some intentional structure, I would argue you can't even check this. So if you said, well, I'm going to use a refining example. I have 2 HF alkylation units. I have one in the Middle East and one in the great United States of America. If I looked at those 2 evaluations, how do they compare? It is almost impossible to know the same scenario, the same cause, that we had the same control valve that went closed and we evaluated that scenario for the facility in the United States and evaluated the same scenario in the Middle East. It's tough to even find whether we evaluated the same scenario, let alone did we even come to the same conclusion. Did we think that what was going to happen was going to be the same? Or did one team feel like it was a really minor severity and another team thought that this was going to be catastrophic? I know we're all engineers and we're all incredible thinkers, but believe it or not, this is sometimes not clear. It isn't always obvious how you should come up to these consequences. So that would be the same process. What's also interesting is if you looked at the same technology, such as a chemical facility. So if you are a large petrochemical owner-operator and you have a technology that generates one type of plastic and you have 10 of these plants scattered throughout the world, how does the risk look like for those 10 different plants? Can you even compare them? Can you even pull them out of your PHA repositories, that shelf, that photograph album, and start to compare them? So if you start to think about, well, yeah, we really can't do that, but if you started to change your paradigm of how to structure your PHA data, what could you use that information for? Here's just a couple thoughts. What if you could understand the risk profiles of your units? Right now, if I asked you what's the highest risk unit you have in your facility, and I asked 10 different people at that facility, I bet that they would all say the same thing. However, if you look at the data, you would be shocked to find out that that may not necessarily be the case. We have found with some clients at large petrochemical plants that they have similar risk profiles, meaning a scenario has a certain unmitigated risk, or all the scenarios have an average unmitigated risk in a tank farm as they do with a highly toxic, flammable material. On the surface, is that right? Doesn't sound right, but is it? I'm not passing judgment, but it may or may not be. Also, if you have different evaluations, ultimately we said that you're going to have recommendations. You're going to try to go change things in the field to mitigate your risk. If someone overestimated the risk versus another facility of the same style, you're going to go spend money correcting something that another plant felt you didn't need to. One of those isn't right, and you're going to spend money to try to fix it. Also, if you had all this information in one spot, just think of how valuable that could be for everyone to be able to access it and know how to review it. When you have those analytics, so now you categorize it, you could run some analytics to do some pretty cool stuff. You could say, hey, every time that we overpressure a distillation column, what's in our whole corporation, or even at one particular plant, every time we overpressure a distillation column, what's the most frequently employed safeguard? Is it relief devices? Is it operator alarms? Is it basic process controls? Now, should they all be the same? Probably not, but they shouldn't all have, it shouldn't be a scatter plot. And so you should be able to start to look at the analytics, because this is kind of a big data picture, and start to run some pretty interesting information. Okay, so then, what does the solution look like? So the first, start with the structure. So we showed how PHAs currently structure the information. We're going to show you what we have used with some of our clients to really make their PHA information pop. So same thing as what we had before. Same example. You could see the information in that good old Longhorn orange is the information that was captured previously. And here is some suggestions of where we think you should increase the information captured, such as, for this scenario, you could say, here's the technology, here's a cause category, here's the process fluid, and here's the location. So if you captured that, essentially it's breaking out some of the information that is in free text fields and capturing it more accurately in your cause. You could do the same thing with your consequences. Well, this was a tower overpressure. That's embedded in your free text consequence, but you really don't have a way to break that out. But if you just added an additional field to what you're capturing, you could capture the information to allow you to start to cross-compare. And we'll show you what that looks like in a minute. Your safeguards. So this is probably done better in the industry than the cause and the consequence, but even this, even though done well, could use some improvement. So you could say, okay, we have a shutdown. Well, that is a safety instrumented system. It may be a basic process control. You also have a relief device. You could break that out and say this is a pressure relief device, because some people, one team may put RV305, one person may say relief device 305, and some may just say relief device on the debutanizer. There's no consistency. You may not need that consistency for some of the analytics we're going to suggest if you simply captured the category and type of that safeguard. So once you improve that structure, then it allows you to run some interesting analytics. So some of these things is we've now identified categories of what could go wrong and what was the end result. So what are the different things that can go wrong, i.e. the causes, and then what is the end result, and we categorize those as well. That allows us to identify a lot of really interesting information. So I'm going to show you some of that. So if you look at these two systems, identical systems, two separate plants. They're both a blocked outlet. The process fluid was butane on the overhead of the butanizer. If you captured that, you could take one from the Middle East and one from Tennessee and say, these are the same scenario. They're in the same technology, they're same cause category, the same process fluid, and they're same similar equipment. What happens when we compare those scenarios? Well, you document what happens in the consequence. And this is a real-world example. We actually see this with clients. One evaluated it differently. They estimated the overpressure differently than the other. One essentially said, we're going to have a catastrophic vessel failure, and the other said that, oh, this is going to be a gasket failure. Now, which is appropriate? Interestingly enough, ASEG has a book called that has a book that specifies which way to evaluate this. It's a great book. But obviously they didn't reference that. But this would be a way to help identify that the evaluation methodology was different. You don't know if you have a different evaluation methodology until you're able to compare similar scenarios. And in today's PHA landscape, it is almost impossible to compare similar scenarios without incredible amounts of work. Additionally, your safeguards. Once you do find out what the consequence is, it's always interesting to compare how do different teams mitigate those risks. So some teams may choose, one of the members of the team may be a relief system expert. And because this person has sized relief devices for the majority of their career, every time they have an overpressure, they're going to say, man, let's do a relief device. I can confirm it was sized for that. And they just have a bias. Versus another team may have an instrument person in there that has spent their entire career doing safety instrumented systems. And so it's not that one's wrong or right, but it is interesting that you may be mitigating the exact same scenario in different ways. And so when I think about safety instrumented systems versus a relief device, I don't lose too much sleep over that. But what if I said that they mitigated it with alarms or procedures and it was catastrophic? Does that feel right? If one plant said we're going to rely on our procedures and another plant said we're going to rely on a highly engineered safety instrumented system, just doesn't feel right. Not to mention the cost of those, those are a tad different. So you need to be able to compare these scenarios. Again, the mitigated risk, when you start to look at all this, you can start to compare the mitigated risk, the unmitigated risk, and the mitigated risk, but you have to have a way to associate them. And the only way to associate them is to really improve the way you capture this information. So, another way to look at this, here's the big picture of comparisons. This consequence is the same consequence. You lost feed to a similar column. Here we just said that it was column 1. It might be column 1 in one facility and column 3 in another. It might be a debutanizer in one and column 4 in another. But nonetheless, the way you would compare it is in the categories of that cause. And you can see that this exact same consequence may have shown up in a lot of different ways and have significantly different unmitigated risks and mitigated risks. Kind of what we were mentioning earlier. This is just a picture of how that would surface. Here's an interesting picture of how that would surface for how you mitigate your risk. You could say, okay, here's all of our unmitigated risks. So we have in the red any scenario or group of scenarios that had an unmitigated risk of 5. What do we use most frequently? We use relief devices versus what do we use most frequently for 4s. Now, when you start to collect all this data together, you got to remember that Polaroid picture versus this gigapixel zoom in, zoom out. You could do this exact same analysis for a facility and say, hey, for the Tennessee plant, what do they use most often for unmitigated 5s? Do they use relief devices? What does the Middle East plant use? And you could say, oh, for unmitigated 5s, they use procedures. So by zooming in and out of your PHA data, because now you've structured it in a way to allow you to do that, the analytics start to really get pretty interesting. These next couple slides are a little bit of that zoomed out view. So if I just look at that Tennessee plant, then this is kind of a demonstration that really illustrates the quantity of scenarios that started in each of the different areas of our risk matrix. So you can see there was at the entire plant, there was 142 of the highest risk items, 142 scenarios. You could average all of these, and you could say, hey, I have an unmitigated risk value. The majority of my scenarios have an unmitigated risk of 3.4. You could do the same by looking at the mitigated risk value. So the mitigated risk is with your safeguards applied. And the difference between that is essentially your risk reduction. So now, because you can zoom in, zoom out, you could look at one specific plant and say, what's our average unmitigated risk? Oh, well, it's a 3.4. What is the mitigated risk value? It's a 1.9. That means that we are average on most scenarios, we're reducing our risk 1.5 levels. So it gets really interesting if you looked at it through a couple different lenses. Again, this zoom in, zoom out that you can't do unless you organize your data differently. Overall, what's our corporate risk look like? Well, this is the same technology. This is the same type of a plant. We have 10 of them throughout the world. Whenever we look at the aggregate data, we have a 2.7 unmitigated risk. We have a mitigated risk of 1.7. That's a residual risk of 1. Look at two separate facilities. Plant 1 has a risk reduction value of 0.6. Plant 2 has a risk reduction of 1.5. If these are the same technologies, similar throughput, does that sound right? It probably isn't right, but that's the limitation of your current information. You can't even run those analytics. So, what do? Well, you connect this in a manner that big data is incredible at. So you start to organize it in a way to where you can analyze it, and then you start to just ask questions. Well, I wonder if I have any alarms for more than one scenario. How many times do I use a specific alarm? Moreover, for the highest risk scenarios in my company, how do I mitigate them? Do I mitigate them with alarms? Do I want to mitigate them with alarms? You can ask those questions, but unless you have better data structures, you can't answer them. And as big data always does, as any test should do, you shouldn't necessarily try to prove a hypothesis. You should have some questions, but let the data lead you to see what is actually the result. Don't bias your evaluation and then manipulate it to come up with an end result. Just gather it and start asking the questions and see where the data leads. It's always good to key in on critical scenarios, so those are most often high risks. And then you can start to determine, hey, for these really high risk scenarios, once we have consistency so we can evaluate them and look at them collectively, how should we allocate our resources? Should we allocate the same resources, time, effort, energy, and cost, to some of the lower risk ones, or should we allocate it to those higher risk ones? I think that's an easy call, but unless you're able to compare it, you really don't know how your risk profile looks. And you don't know whether your risk evaluation was accurate, and simply because the team made a mistake, you may be sending money somewhere you don't want to send it, and more importantly, you don't need to send it. So, some takeaways. You really need to have a paradigm shift to embrace big data concepts for your PHA information. No longer think about a snapshot in time Polaroid picture, but how can you organize, structure that data, capture that data, so you can zoom in, zoom out, cross-compare between facilities, cross-compare between similar failures, and allow you to come to some results and understanding of what that data tells you. And a lot of big data tools can really help move us forward. The nature of this presentation isn't to come up with an architecture of this big data solution, but to show you that you really need to start thinking differently, because PHA data can fit into a big data picture. So I appreciate y'all's time. Just wanted to open it up for questions.
All right. Thank you, Patrick. I do have some questions that we received here. The first question we got was, how would you recommend implementing this in the various PHA softwares that exist, or would it require separate programs like Excel?
So some of the PHA softwares that kind of the leading commercially available softwares have a fair amount of flexibility in what you capture. You can actually create fields and start to capture that information. Where they fall short is then providing the ability to start to cross-compare. And so, yes, you can use your existing tools to capture the information, but then you have to find tools to really use that information, because the quantity of information will quickly exceed Excel's ability. So there are applications out there to allow you to get all that data into one central repository and start to run these analytics. Just coincidentally, Providence has one of those tools, but other big data tools are out there. Ours is focused on PHA information, but yes, if you have a commercially accepted software today, start by configuring your templates to capture this information. That is the first step, and you can do it now.
All right. Next question says, would you recommend going back through past PHA reports and categorizing them, or just starting with new ones moving forward?
So if someone held a gun to my head and said, I have two choices, choose one of those, I would say start as you move forward. Simply because you're already going to be doing it, and what we have found is when we facilitate these PHAs, it does not add incredible amounts of cost to the study. So if I had to choose that, if it was a binary choice, I would say start now and improve. However, just think if you started to go back and provide these categories so you can start to cross-compare your historical information. Now you're able to leverage 25 years of some of the most incredible information you have captured. So you can then go back and say, hey, what did we say about overpressure of distillation columns in the 2000s, from 2000 to 2005? So yes, I think there is incredible value in going back and doing this for your previous PHAs. A lot of our clients, they'll have an incident. And then, of course, everyone likes to ask, what did the PHA say about that incident? Did they predict it? They'll go back to the most recent PHA and say, man, we overlooked it. Well, what about the one before that? Nope, they overlooked it too. 3 ago, we captured it. So that means that a cause, the initiating event, was captured 2 or 3 PHAs ago and somehow got lost. If you had this ability to kind of cross-compare, you would say, hey, we've got this cause, we have this scenario that hasn't appeared again for 2 more cycles. Did we change our plan? Was this just an oversight? Did it get lost in the revalidations? There's huge value in doing it to your historical information, but if you only have one choice, do it on the stuff you're already doing because you're spending time, effort, and energy already.
Okay, looking through for the questions. Can you clarify when you mean no structure to data?
So the big problem when I say that there's a kind of a limited structure or a lack of structure to the data, it's getting primarily the fields for PHA where there's very little structure is in the cause and consequence, and those are free text fields. So if you think about, hey, I'm going to talk about how a car accident could happen. Well, a car accident could happen because someone runs a stop sign, or they don't perform proper maintenance on their vehicle, or they are driving while intoxicated. You can imagine that if you were going to document all the different ways a car accident can happen, and it was just free text field capturing the way that you talk, that's not a very helpful set of data, because then you have to be in the mind of the person that wrote it. Now, there's incredible machine learning out there, and there's a lot of growth in how to use kind of that free text, even so much as using the recorded spoken word. However, that technology has a long way to go, and so unstructured data is really capturing information without any data mask. So it's what would be an improvement is, well, we could have something go wrong, and it was because a valve with this process fluid happened at this location, versus just free text, oh, a manual valve was inadvertently closed by an operator on the debutanizer overhead line downstream of FE 101. Someone else could simply say, oh, we blocked flow on the overhead of the debutanizer. Well, for someone to be able to compare the results of those two evaluations, you have to read it. And again, machine learning is coming a long way, but I have yet to see machine learning that's able to capture and cross-compare those. So unstructured data is just really free type texting. We're suggesting add additional categories that allow you to cross-check the scenarios.
Okay, it looks like this question, I believe it says it's in reference to the PHA comparison slide. I believe it's slide 34. They ask, should both have been evaluated by PHA, and therefore both are flawed? I think that's what it says.
So here is a comparison. I'll go to slide 30.
It might have been a little earlier.
Yeah, so I think 32 is probably the best illustration of comparing two scenarios. So essentially it's the same failure. What I'm arguing is right now PHAs are doing an excellent job at documenting that failure. However, the way that the documentation occurs is you have no way to compare between two similar facilities that evaluation. So if you capture some additional information, in this case specifically about the cause, meaning we had a blocked flow on this process fluid, happens to be butane, of the overhead of the debutanizer, you capture that information, now you can cross-compare. When you do that, this plant in Tennessee, I'll call that plant 1, and plant 2, the one in the Middle East, evaluated the exact same scenario in a fairly different way. One said that we're going to achieve an overpressure of greater than 3 times. Another said, hey, we're going to be somewhere between 1.1 and 2 times the maximum allowable working pressure. One said we're going to have catastrophic vessel failure. Another said you're going to have gasket failure. Now, just for giggles, indulge me. Let's say that gasket failure is the right evaluation. I'm not judging which one's the right one. That's a really fun conversation to have over a beer, but let's say that gasket failure is correct. The vessel failure overstated the risk. So now that means that if you didn't have a relief device or a shutdown system and you were unmitigated risk, too high, unacceptable risk, you went and spent money to go do something to mitigate that risk when in actuality, the scenario, the evaluation technique was flawed. So you're going to go spend money on somewhere you shouldn't. Conversely, apply it the other way. Gasket failure could be understated. Now you're not going to go do anything. You're not going to necessarily maintain your controls around that system. You may not have a safety instrumented system. You may set the maintenance of that relief device a little bit lower. And so now, because you have two separate risks identified, you have injected, whether you realize or not, you have injected additional risk because you're evaluating it separately. So that is how, so this is an evaluation of the same scenario at two facilities. That's what that is demonstrating.
Okay, I think based on the time, this might be the last question. On the risk classification, would additional levels of risk classification possibly help? For example, if consequences are evaluated in 7 levels as opposed to 5?
So I think the more granular you get, there's probably some increase in value, but the one thing you also need to remember is a lot of companies typically have different measurements for each one of those risk consequences. So they will look at the consequence and they will rank it not only in 5 areas, but those 5 areas have subsections of personnel risk, environmental risk, sometimes economic risk. So they will say, hey, what's the consequence to personnel? What's the consequence to environmental? So there is already one additional step, one additional level of granularity. But I think the question is more about will you improve with more measurements? And I think that there is a happy medium. Obviously, good or bad is too broad, and 1 through 100 is too granular. From what I've experienced in the industry, somewhere around 4 to 7 is appropriate. So we use the example of 5. So short answer, yes, the more granular you get, the more exacting you'll be, but then the more work you have to really refine your evaluation down to that particular consequence. And PHAs and other techniques that fall into the PHA realm, HAZOP, LOPA, what-if checklist, are really an order of magnitude evaluation. And if it doesn't pass that order of magnitude evaluation, then is when you would sharpen your pencil and start to get a little more exacting. But for HAZOP, LOPA, 5 to 6 seems quite appropriate.
All right. Thank you very much, Patrick. That will be all the time we have for slides as we've reached 3 o'clock. If your question was not answered, please feel free to send it to producer@aiche.org. We will compile answers to the questions to try to get all questions answered, and those will be available with the slides to all the attendees. Thank you for joining us. To replay this webinar or view any others, you can go to www.aiche.org/webinars. As we mentioned previously, it'll take roughly 3 to 4 days for these recordings to be posted to your stuff. And to download your PDH certificate, you can visit the webinar page on the Academy website and click on the link provided. Thank you very much, Patrick, for your very interesting presentation, and thank you everyone for joining us today.